Hello everyone, I'm Medyamera Karataş and today I will talk about the YOLO algorithm for object detection. Firstly, what is YOLO? YOLO is the abbreviation of You Only Look Once. YOLO algorithm is based on regression. So what's the regression? Regression is a technique for investigating the relationship between the independent variables and dependent variable or outcome. YOLO, based on regression, instead of selecting the interesting part of an image, it predicts classes and bounding boxes for the whole image in one run of the algorithm. In other words, it scans the whole image and makes predictions to localize. It identifies and classifies objects within the image, and algorithms are faster for real-time object detection. To understand YOLO algorithm, first we need to understand what is actually being predicted. YOLO uses deep learning algorithms for object detection. YOLO has superior properties than other old methods. For example, RCNN, which is mostly used method. These are the differences between the YOLO and RCNN. YOLO classifies certain objects within the image, while RCNN focuses on a specific region. YOLO is faster, but RCNN is slower. YOLO is applicable to real-time, and RCNN cannot be implemented in real-time. I will give details in later slides. And YOLO is easier to optimize, and RCNN harder to optimize. YOLO has three main structures. One algorithm, second network, and three loss function. And I will give details about, I will explain each of them. Firstly, YOLO algorithm. In the object detection, we usually use a bounding box to describe the spatial location of an object. The commonly used bounding box representations is XY axis coordinates of the bounding box center and the width and height of the box. And there's also confidence score. It's the probability that the box contains an object and how accurate is the boundary box. A bounding box is an imaginary rectangle that serves as a point of reference for object detection and creates a collision box for that object in projects on image process. Typically, most of the bounding boxes does not contain an object, so the prediction is needed to use. YOLO algorithm divides given input image into the SS grid system, as you can see in here. Each grid on the input image is used for detection. The grid cell predicts the number of boundary boxes for an object. The process called non-max suppression can be used to remove unnecessary boxes with low probability to contain objects and those that share big areas with other boxes. Algorithm is based on regression where the object detection and localization and classification, the object for the input image will take place in a single go. This type of algorithm is commonly used in real-time object detection. This is the good image. It shows the end result. In here, it's related to YOLO 1 version. YOLO V1 uses convolutional implementation of sliding windows for bounding box prediction by using 1-1 kernels, as you can see in here. Instead of running forward propagation on all individual sliding windows of the input image independently, these windows can be combined into one forward propagation computation and share the computation in the common regions of the image. YOLO V1 built on this approach to predict exact bounding boxes. It splits an image into grid cells, assign object boxes to a specific grid cells based on the center pixel of the box, and defines an output vector with, for example, k number of classes. PC can be interpreted as objectness. The probability that there is an object in the bounding box. Bx and By defines the center of the bounding box, and Wx, Wy, its width and height. Related to the grid cell, C1 and C2 represent the conditional probability of class 1 and 2, given that there is an object. The network. YOLO network is structured like a regular CNN. It contains 24 convolutional and max pooling layers, and then 2 fully connected CNN layers. Leaky ReLU is used as an activation function. YOLO is a clever convolutional neural network for doing object detection in real time. The algorithm applies a single neural network to full image and then divides image into regions and predicts bounding boxes, as I mentioned before, and probabilities for each region. These bounding boxes are weighted by the predicted probabilities. YOLO is popular because it achieves high accuracy while also being able to run in real time. This is the RCNN network. The region-based convolutional neural network, RCNN, works by initially applying the selective search algorithm to find region proposals, as Jonathan mentioned. The proposals are then extracted and warped to a standard size, so they can be processed by a neural network. Next, a standard convolutional neural network is applied to classify the images into one of the several classes. But there are problems in the RCNN. Because it takes a huge amount of time to train the network, as you would have to classify 2,000 region proposals per image. It cannot be implemented real time, as it takes around 47 seconds for each test image. The selective search algorithm is a fixed algorithm, therefore no learning is happening at that stage. This could lead to the generation of bad candidate region proposals. I mentioned CNN convolutional networks layers in both network and RCNN network also, YOLO network and RCNN network. So why are layers used in CNN? This enables the CNN to convert a 3-dimensional input volume into an output volume. Convolution, pooling, normalizing, and fully connected layers make up the hidden layers. Multiple convolutional layers are used in CNN to filter input volumes to higher levels of abstraction. What is convolution layer used for? A convolution layer transforms the input image in order to extract features from it. In this transformation, the image is convolved with a kernel. A kernel is a small matrix I mentioned in the formal slide, with its height and width smaller than the image to be convolved. It's also known as convolution matrix or convolution mask. Why do we need convolution layers? Convolution layers have been used for a long time, typically in image processing, to blur or sharpen images. Now I will mention loss function. One of the bounding boxes should be responsible for the object within the image, since YOLO algorithm predicts multiple bounding boxes for each grid cell. To achieve this, the loss function is used to compute the loss for each true positive. To make the loss function more efficient, the bounding box with the highest intersection over union with the ground truth is needed to be selected. This method improves predictions by making specialized bounding boxes, which improves the predictions for some aspect ratios and sizes. The loss function of YOLO is the sum of the following 5 parts, as you can see from here. This means that the jth bounding box predictor in the cell I. Lambdas are used to remedy the problem of imbalanced data. In the part 2, you can see the square root of the width and height are used. Since the same prediction error of width and height has different influence for small box or large box, the square root can amplify the influence when the box is smaller related to large box. YOLO has 7 versions and also 1 YOLO Lite versions. YOLO Lite version is for the non-GPU computers for the real object detection. YOLO V7 is the fastest and most accurate version of the YOLO. In my presentation, I will mention V1 and V2. YOLO V1. The first version of YOLO V1 was introduced in 2015. It used a limited darknet framework that trained on ImageNet dataset. This dataset has many limitations and restricts the usability of YOLO V1. YOLO V1 struggled to identify small objects that appeared as a cluster and was inefficient at generalizing objects in images that had different dimensions than the trained image. This resulted in poor localization of objects within the input image. That's why YOLO V2 was developed. YOLO V2 was released in 2016 with the name YOLO 9000. YOLO V2 used darknet 19, a 19-layer network with 11 more layers charged with object detection. YOLO V2 is designed to take on the faster RCNN and SSD, which showed better object detection score. YOLO V2 upgrades over YOLO V1 include improved mean average precision. The newer high-resolution classifiers increased input size from 2224 times 2224 to YOLO V1 to 448 to 448 and improved mean average precision. Secondly, better detection of smaller objects. It divides the image into smaller grid cells to improve localization and identification of smaller objects in the image. Improved detection within images of varying sizes, training the algorithm with random images of different dimensions to improve the network's prediction accuracy of objects from input images of different dimensions. And lastly, anchor box. Anchor box is a type of the bounding box, specific bounding box. It provides a single framework for classification and the prediction of bounding boxes. Anchor boxes are designed for specific datasets using k-means clustering. Why YOLO faster than RCNN? In practical, and also faster RCNN. In practical, it runs a lot faster than faster RCNN due to its simpler architecture. Unlike faster RCNN, it's trained to do classification and bounding box regression at the same time. The mean average precision of faster RCNN reached 80%, but YOLO V3, for example, had a significant advantage in detection speed where the frames per second was more than 8 times than that of faster RCNN. This means that YOLO V3 can operate in real time with a high mean average precision of 80%. So that's why YOLO is preferable. The speed advantage of YOLO comes from its ability to run the whole image through the network once, split the image into grid cells, and predict whether an object is present or not. That's why CTL YOLO is most preferable one. In conclusion, YOLO is simple to construct, and unlike classifier-based approaches, YOLO uses a loss function. It provides a real-time response and real-time object detection. It's really fast, and it's a neural network for the real-time detection and tracking of multiple classes of objects. The precision of the algorithm could be improved with training on bigger and more diverse datasets. This is my reference list, and thank you for your listening.
Okay, great, Merve. So
yeah, I try to give details a lot, especially for what is the layers, what is the bounding box. Yeah.
No, it's significantly improved from the time you showed me your presentation. So I got some questions.
Mm-hmm.
First of all, why YOLO is called YOLO? You only look once.
Yeah, this means that, as I mentioned before, it's algorithm based on regression, and it scans whole image and make the prediction localized. That's why I can say it's just for a single go, and direct scan whole image and localize, and then actually it does everything at the same time, one single go. That's why classification detection. That's why it's you only look once.
So right. So if I give you an image, so where you have the image of the grid, can you point to that slide for me?
Which one? This one?
Yeah, or maybe the next one.
This one?
Yeah, this is good. So here we're talking about the prediction vector.
Yes.
So it is the information that we are getting from your network, from your algorithm after you run. And this prediction vector, it contains the information about the bounding box.
Mm-hmm.
So here on screen, you have divided your YOLO into 7 grids, 7 by 7. So can you divide it into any number of grids in YOLO V1, or is it fixed?
Actually, YOLO V1 is, I remember something like that, is YOLO V1, I guess, S times S grid. But in the YOLO V2, because YOLO V1 cannot detect the small objects, that's when YOLO V2 was developed, and it's 13 times 13 grid. In this way,
That's correct.
it can
That's
detect
absolutely
smaller.
correct.
Yeah, that's
So
it's
on YOLO V1, you do
one.
7 by 7, and in YOLO
Yeah.
V2, you do 13 by 13. Good.
Yeah.
Now you divide the image into these many grids. And now how do you predict these bounding boxes? So you are, because while training, you are just providing bounding boxes while training. Now, what is the next thing? Your algorithm, it sees the image, divides the image into the grid, and then what happens?
Okay. Firstly, it how can I say, divides the grid cells, and these grid cells based on the center pixel of the box and defines an output vector. For example, key number of these ones. These are kernels, and we use PC. I mentioned PC can be interpreted objectness and probability. There is an object in the, how can I say, if there is an object in the box or not. Actually, it's the probability of this. Defines the center of the bounding box, Bx, By, and Wx, Wy is width and height, of course, because it's a three-dimensional object. And then C1 and C2 represent the conditional probability of the class, given that there's an object. For example, if there's an object at there, if there's no object at there, because YOLO, how can I say, delete this, there's no object in here. How can I say, probability is low with there. Being an object in here, probability of being an object in here is low. That's why YOLO disregard these kind of things. That's why PC is important, actually. Probability of the various image.
Your point is that it sees the object, divides into the grid, and then into each grid, it gives you an objectness score. And if the objectness score in each grid, so for example, in the center grid, there is a football. So in that grid, it gives an objectness score of 1 because it's sure
object,
that
there is object, yeah.
An object. And then it is also going to look at conditional probabilities, which is, it will tell which object is it from the classes that you defined. Okay, is it is it is it a football, or is it a player, or it's some kind
pedestrian, for example. I found some articles related to this one, for example, in the traffics, pedestrians or cars. And
then what happens is, once it say the grid, first of all, you give it an objectness score, and some grids there is no objectness score because there is no center of the object. It checks for the class probabilities, that what kind of object is there. And then it tries to create and predict the bounding box depending upon the class object it is there. And then it predicts a bounding box, right? And that bounding box could be,
actually, it's a special position of the images in this, how can I say, space system. We can say that it's a, how can I say, imaginary rectangle bounding boxes.
It's an imaginary rectangle, or it's a bounding box that it predicts, but then it will optimize the prediction based on the training, right? And there it uses regression, right? You told that regression is something in the beginning of your presentation.
Yes, it's a technique for investigating the relationship between the independent variables or dependent variable or outcome.
So it is something that is a technique trying to have a relationship between independent and dependent variable, right? And then it tries to do a regression between what was already defined versus your variables here that you are predicted. And it tries to do an optimize based on regression between the bounding boxes, the predicted one and the final and the trained one. And then it predicts the bounding box. Now, In YOLO V1, there are how many bounding boxes per grid that it predicts?
I guess I said the 24. This one is related to where is the convolutional max and back spanning layers and 2 fully connected CNN layers. I guess this one.
Yeah. Now, like each grid, it produces how many bounding boxes? It produces 2 bounding boxes, right?
Yeah, yeah.
Right. And then what are they doing in YOLO V2? How did they change the architecture of YOLO V2?
Yeah, it's a good question. I mentioned in my slides also. Yeah, for example, YOLO V1 upgrades over YOLO V1. YOLO V2 upgrades over YOLO V1 include improved mean average precision, better detection of smaller objects, improved detection with an image of varying sizes, and anchor boxes. So what does that mean? For example, in the YOLO 1, input size, for example, 224 times 224. But V2 has a higher input size, like 448 times 448. For the better, I mentioned actually this one. It's, how can I say, it divides the image into a smaller grid cells, 13 to 13. This is also another superior properties V1, V2 to V1, because in this way, its identification of smaller objects can be easier. The other one is improved detection within the image of varying sizes. It's training the algorithm with random images of different dimensions to improve the network's prediction accuracy of objects from the images of different dimensions. Because YOLO V1, how can I say, it's hard, for the YOLO V1, it's hard to detect different dimensions actually. And anchor boxes provides a single framework for classification and the prediction of the bounding boxes in the YOLO V2. These are the actually new ones in YOLO V2. There's no, I mean.
Could you elaborate on the concept of anchor boxes? Now, you know that in YOLO V1, you saw that it got divided into the grid, you find the objectness score, and regression is based on the ground truth box. Now, what is happening in the concept of anchor boxes?
Actually, anchor boxes provides a single framework for classification and prediction of bounding boxes. It's a specific bounding box, actually. Anchor boxes are designed for the specific data sets using k-means clustering.
So what happens is like, so what is the difference between like bounding box and anchor box?
Anchor box actually is some kind of prediction of, how can I say, as I mentioned, I said this one. Anchor box is actually type of bounding box, but specific one.
What happens is
single framework. It's a single framework.
Yeah.
And the prediction of bounding box actually.
So what was the problem in YOLO V1 was that if you find the center of like 2 objects have the center in one grid, then there is a problem in YOLO V1. For example, if there's a grid and it contains football as well and the player as well. Now, for example, a player is holding the football. Now, in that case, the center of the object belongs to the grid, but the grid can only produce one class. There, where the YOLO V1 failed. And then the concept of YOLO V2 came. Then they introduced like what we do. Then they introduced the concept of anchor boxes. So what happens is anchor boxes are kind of predefined boxes that you give, as you said, on the basis of k-mean clustering. So you define the sizes. For example, in our case, we will have a lot of voids and bubbles. So we will define, some kind of anchor boxes. And once we define those anchor boxes, then we tend to, after defining the predicted anchor box, would be optimized with respect to the predefined one. So in that case, it solves the issue because in YOLO V2, a grid can predict 2 different kind of objects and 2 different kind of classes. So that was the improvement. There where YOLO V1 failed. Yeah. This was the main improvement. Now, I think One thing that's a small question. Did they train YOLO V1 using the darknet? Because I remember they used GoogleNet for YOLO V1.
Actually, I checked this one and I saw it seems that the darknet framework. And this uses darknet framework with ImageNet 1000 dataset, but YOLO V2, darknet 19. I checked this once again and I found information.
So cross-check that YOLO V1 is based on GoogleNet.
Yeah, I remember. Yeah, there is also GoogleNet uses one. I saw it.
Okay, yeah. Right. Okay, that concludes, I think, your talk. I think it was well presented. Thank you. Thank you so much.
Yeah, thanks.
Right, Julie, do you have any question? It's good.
I don't.
Okay, great.
Next week's presentations are 14 and 15, right?
They are the same day, 4th and 5th, sorry, Thursdays and Fridays at 4 o'clock.
Okay, so
Yeah.
15 and 16.
Yeah.
Okay. Okay,
Right.
thanks.
Bye. Take care. Bye.
Bye.
Bye-bye.